Hey, our topic today is the derivative and the infamous tangent line problem. Infamous tangent line problem. This is one of the reasons calculus started. This corresponds to section 3.1 in our textbook. So the first thing we got to do, kind of identify a keyword there, tangent line. Kind of a buzzword. When you see a tangent line, you should be thinking of slope. And then we're going to go one step further. When you see slope, you should also be thinking of derivative. So you want to kind of get those three ideas interchangeable and synonymous in your mind. When you see tangent line, think slope. When you think slope, you should also be thinking derivative. Those three ideas kind of blend them together. One kind of usually sometimes means the other. When you see one, you could interpret it as another for a method for completing the problem. So some examples of tangent lines. Tangent lines are to a point on the curve. They describe the rate of change. So this parabola, we have the tangent line at the maximum. At the maximum, the rate of change is 0. So the tangent line is a horizontal line with a slope of 0. Think about when you throw a ball up in the air. For just an instantaneous, one single instant, one moment, that ball going up, and then before it comes down, it stops. For just a bare instantaneous instant, that ball stops, and then it comes down. So, tangency at a point. This curve going down, the point P is on the negative part of the curve, and the curve is decreasing, so the tangent line is negative, has a negative slope. This example here, point P is on the increasing interval of the curve, so the tangent line is increasing also, has a positive slope. In geometry, we talked about tangent lines to circles. So you have a circle that exists, and you have a tangent line just grazing the circle at one point. The point where it meets is the point of tangency. In calculus, there's a tangent line, there's a point of tangency, but the point of tangency should represent the curve's rate of change at that point. So in this example, line L intersects the curve only at one point, point P, but the slope of the tangent line does not describe the rate of change of the curve at point P. So line L is not a tangent line. In geometry, a tangent line to a circle only intersected the circle once. In calculus, the tangent line can hit it more than once, but at one of those points, it should describe the rate of change. So line L, horizontal line, at point P, the curve has a 0 rate of change, and then the point as the line goes on, the curve changes direction to intersect it, but at point P, so that location at point P, L is describing the rate of change. This example here, it touches at one point, but does not describe the rate of change again. Over here, again, you can cross the curve. At that point, line L describes the rate of change. It doesn't describe it at every point, but at that point, point P, it does. So now the infamous tangent line problem, okay? So this is where algebra kind of falls short. Algebra is really good at looking at linear functions and the slope of linear functions. When you get to a curve, not so much. So let's say that we have a curve and we want to look at the rate of change. So we want to look at the tangent line at this point. So we'll draw a tangent line right about there. That's good enough. So the rate of change, what is the slope of this line? Well, the algebraist says, hey, I need 2 points in order to calculate slope. Rise of a friend, delta y over delta x. y2 minus y1 over x2 minus x1. You need 2 points, 2 separate discrete points. So you have the point of tangency. We'll call that C, comma f of C. And going over to the right, we'll go here. In this point, let's see if I can kind of zoom in closer. So I can have small line of writing. We'll call this the point C plus delta x. So we're moving so far to the side. So our point C plus delta, some change in x, so delta x. Our y coordinate, f of C plus delta x. So, from the red point of tangency up to the other point, we have what's called a secant line. So a line that will describe the average rate of change, but not the true rate of change at an instant. So from our point of tangency over to a new point, that is our change in x, so delta x. Then the red, of course, right here is our tangent line. And the algebraist will then use that secant line, so the dotted black line, the two endpoints, to calculate the slope. Now that black dotted line, that red tangent line, they're both positive, and that's about all they have in common. So there's this gap between them. That is a difference in their slope. So it's an approximation, but it's not entirely accurate. So the algebraist does the method of exhaustion. Goes, okay, if I got that, can I do better? Let's see if I can copy some of these fine illustrations over. It's all kind of blended together. We'll try it. That's pretty good. Kind of zoom in. Erase what I don't want. Okay. So, method of exhaustion says, hey, if we can, let's get closer to our original point. So we won't have such a big delta x. Instead of going 3 units over, we'll only go 2 units over. So up to here. So I can copy more over. So the idea is, if our original problem got us a pretty good estimate, can we get an even better estimate? So this is our secant line. And if you found the slope of the secant dotted black line, the slope of the red solid tangent line, they would be closer than previous. But there's still a problem of this gap between the two. Now the gap is smaller, but it's still there between your tangent and your secant. So the algebraic says, okay, can I get even closer? Let's see if I can do this again. So can I get even closer to what the exact value? Essentially, can I get so close that my point of tangency is also both of my endpoints of my secant line? So now you only have one point to find the slope of. So let's go ahead, let's find the slope. Slope, as you know, is delta y over delta x, so y2 minus y1 over x2 minus x1. But in this case, y2 and y1 are the same point. x2 and x1 are also the same point. So f of c minus f of c gets you 0. C minus c gets you 0. So we get what's called the indeterminate form. And this is like the algebra person's worst nightmare. Okay, so you get indeterminate form. When you go to find the slope, you 0 in the top, 0 in the bottom, you can divide by 0. That's a problem. Okay, so what is an algebraist to do? Like, the slope can't exist. But if it could exist, hypothetically, what would it be? So this is where the calculus comes in, the idea of limits. No, this can't exist. You can't divide by 0. But if you could, what would happen? So that foundation of limits in calculus, that foundation allows us to do more than the algebraic could. You have a secant line, but it's far out. It's an estimate, but it's only an estimate. So you bring the secant line closer, but it's still only an estimate. Eventually, you bring it so close, it's the same point. But algebraically, you're dividing by 0. But if you look at the idea of limits, kind of that delta x, bringing it down, 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 so delta x is approaching 0. We get a definition for slope using limits. Now this slope formula, wow, that brought me back up there. Come on down. Okay, now this slope formula still has y2 and y1. So this is y2, this is y1. It still has x2 minus x1. But you see in the limit notation, we want delta x to be approaching 0, getting smaller and smaller. So as our denominator gets smaller and smaller, what happens to the fraction overall? What would happen if it could be 0? No, it can never be 0. But as it gets closer to 0, what can we predict reasonably would happen? So let's take a look at this. So find the slope of the graph of 2x minus 3 at the point 2, 1. Now this is a linear function right here, okay? Y'all should know what the slope of that line is, okay? The slope should be 2. But using the limit definition, let's take some validity, let's check. See if we do get 2 using the limit process. So the limit as delta x approaches 0, f of, now at the point 2, 1, so at x equals 2. So that would be our c value. So 2 plus delta x minus f of 2 all over delta x. Now, limits. Try to plug in 0. Try direct substitution. Plug in 0 for delta x. Get 0 in the bottom. Oh, shoot. Direct substitution doesn't work. So let's go ahead and do the limit. Try to expand the numerator so that we can get a delta x that we can factor out of the whole problem. Remember, if delta x is your problem, you want to try to get rid of your problem factor. So plugging in 2 plus delta x into the original function for x, it's going to use some brackets to try to organize this a little. So instead of 2x, 2 quantity 2 plus delta x minus 3 minus f of 2. So 2 times 2 minus 3. Can we extend this line all over delta x? So you see the x here, 2x minus 3, 2x minus 3, 2x minus 3. So just plugging in 2 plus delta x for x in the first bracket, plugging in 2 for x in the second bracket. So let's go ahead and work through it, see what happens, expand out, simplify. So we haven't evaluated the limit yet, so we're going to keep that, alright? So distributing 2 times 2 plus delta x, so 4 plus 2 delta x minus 3. That is our first set of brackets. Minus 2 times 2 is 4 minus 3. It's our second set of brackets. All over delta x. Now look what we have. 4 minus 4. Those cancel. We have negative 3 minus negative 3. Those cancel. 2 delta x over delta x. Those cancel also. So bringing this down, we have the limit as delta x approaches 0 of 2. which quite naturally is 2. Hey, we got the answer we should have gotten. Pretty cool, okay? Now let's go for a non-linear function. So x squared plus 1 at 2 different points. And what I'm going to do here is I'm going to use 2 different colors to kind of illustrate the 2 problems and how they really are the same process, even though as you go through the same process you get different answers. So at the first point, at the point 0, 1, so we'll use 0 as our first x coordinate. And at negative 1, 2, we'll use negative 1 for our second x coordinate. So let's go through, let's set it up, the limit as delta x approaches 0 of f of 0 plus delta x minus f of 0 all over delta x. Then right below that, I'll set up the second problem. The limit as delta x approaches 0 of f of negative 1 plus delta x minus f of negative 1 all over delta x. So you see the setup of those two is the same. The only thing that changes is the x coordinate they were evaluating the slope at. Those different x coordinates are 2 different points of tangency. So kind of going through the problems. Good, that looks good. Kind of step by step. So the limit as delta x approaches 0, I'll use brackets here, so bracket 0 plus delta x squared, then plus 1, x squared plus 1, so plus 1 at the end, minus 0 squared plus 1 all over delta x. Do the same step for the red. So the limit as delta x approaches 0 of negative 1 plus delta x squared plus 1. That's our first set of brackets. Our second set, just negative 1 squared plus 1. All over delta x. So again, you see kind of the same steps, just expanding it out. But in the first problem, our x value is 0. Our second problem in red, the x value is negative 1. So now just keep simplifying. The limit as delta x approaches 0 of delta x squared plus 1 minus the second set of brackets, 0 squared plus 1, just 1, all over delta x. The problem in red, since we have binomial to expand, be a little trickier, but just do a binomial expansion. So -1 plus delta x squared. That would be delta x squared plus 2 delta, minus 2 delta x plus 1. Second set of parentheses, -1 squared is 1, plus 1 is 2. All over delta x. And I totally forgot. Kind of in my mind thinking, how did this cancel? And I forgot I expanded the binomial delta x squared minus 2 delta x plus 1. Then in the original quadratic has a plus 1 again. So there we go. That looks better. Now things are going to start canceling out. In the top in black, the plus 1, minus 1, those cancel. Delta x squared over delta x cancel from the top and bottom. So the limit as delta x approaches 0 of delta x. Kind of evaluate that with the direct substitution, get 0. In the bottom, in the first set of brackets, 1 plus 1 minus 2. All those cancel out. Every single term left has a delta x. So squared goes away, this one goes away, this goes away. So the limit as delta x approaches 0 of delta x minus 2. Go ahead, do your direct substitution. You have -2. So different slopes at different points. Algebra, a linear function, had to have the same slope everywhere. With the quadratic, kind of going down, coming up, the slope is different depending on where you are. Vertical tangent lines, they can exist if a function is increasing so quickly it gets vertical. You're going to have a vertical tangent line. Vertical lines don't have a slope, so at those points we say the slope does not exist. And all of this comes to the definition of the derivative. So you'll notice in this definition we have f of c. We have f of x plus delta x. We have minus f of x. Over here, the definition of a tangent line with a slope had f of c plus delta x minus f of c. So at a specific point, c. The definition says at any point x, because if the slope is different and where you look, like up here, at 0, 1, the slope is 0. At -1, 2, the slope is -2. You'd have to do the limit process every time to find whatever slope you wanted. If you do the derivative definition, the limit definition of a derivative of a function, you can find any slope you want. You just choose the next value after you do the limit process. Quick side note on notation. F prime of x, so the apostrophe f prime, dy dx, the derivative of y, bottom, with respect to x. So you're taking the derivative of a function where y equals, but x with respect to, x is your independent variable. Y prime, the derivative with respect to x of fx. In this one, I don't really see it, but the derivative with respect to x of y. So of course, a bunch of different ways to say the same thing. So finding derivatives by the limit process. This happens on the exam, but they don't really want you to evaluate it out. They want you to kind of see it for what it is, tell them what is happening. So find the derivative. Let's go ahead and start. We need the limit as delta x approaches 0. And our formula is f of x plus delta x minus f of x all over delta x. So we're taking this f of x, we're finding f prime of x, okay? I don't like that arrow. Here we go. So, the limit as delta x approaches 0. Let's go ahead and start to plug in some things in. So, x cubed plus 2x. So, x cubed, so x plus delta x cubed plus 2x. So, 2 times x plus delta x minus f of x. So f of x is just our function x cubed plus 2x. And that's all over delta x. So then using the binomial theorem, you should be able to expand to the numerator, work it out, cancel things out. Things should cancel. If they don't, you did something wrong. Go back, okay? The limit definition is a valuable way to work. It should work. If it doesn't, cancel out. You did something wrong. So take a moment to pause the video, do examples 3, 4, and 5, and check your work with my completed notes online before you resume the rest of the video. Kind of one more page we're looking at in this section video, the alternate form of the derivative. So sometimes this alternate form comes up. F of x, the function, minus f of c, the function at the point, over x minus c. So note that in order for the limit above to exist, both one-sided limits must exist. So a lot of what we're looking at, you can use two one-sided limits to look at it. So for example, graphs with sharp turns. So this absolute value function, absolute value x minus 2, you should know from your family of functions that that is an absolute value. Oh, I don't like that. Absolute value shifted 2 units to the right. That's good enough, okay. Now let's get to the graph and find the derivative at x equals 2. So let's kind of look at the two one-sided limits. Let's start with coming in for the left. So the limit as x approaches 2 from the left. So using that superscript. So f of x minus f of 2 all over x minus 2. So let's evaluate that. Okay, kind of work through step by step. No delta, just x. Approaching 2 from the left. So absolute value, x minus 2 minus f of 2 is 0 over x minus 2. So simplifying that down, the limit as x approaches 2 from the left, absolute value x minus 2 over x minus 2. And then think holistically about the problem. So absolute values, by definition, they're always positive. In the denominator, you're doing x minus 2 as x approaches 2 from the left. So number is smaller than 2. So 1 minus 2, 0 minus 2, negative 1 minus 2. The denominator is always negative. So you have negative 1. Something over itself, but the top so is positive, bottom so is negative, you're going to have negative 1. So let's do that again. As x approaches 0 from the right, of f of x minus 2 over x minus 2. Now luckily for you, all of this work is kind of the same. Alright? All the way up to the end. Your numerator, absolute value, x minus 2 is always positive. Your denominator, x minus 2, as you come in from the right, so 5 minus 2, 4 minus 2, 3 minus 2. That denominator is also always positive. So you have positive 1, which looks weird. Okay, that's better. So, from the left, from the right, different values. Negative 1 and 1. Also look at your graph. As you come in from the left, going down, got the slope of negative 1. As you come in from the right, you have this line that is positive slope, so a positive 1. Look at the slope of the black lines, okay? So at this point right here, at 2, the derivative does not exist. Everywhere else it does. At 2, it does not. So we say, can I get this smaller? Okay, so f of x has a sharp corner. At x equals 2. So therefore, f prime of 2 equals d n e. So visually, that's one way you can look at a graph not having a derivative at a point, if you have a sharp corner. Take a look at example 7 also, try that. Check your work and answers with my completed notes. The last thing I want to talk about is this last term. Differentiability implies continuity. Now this is big. Implies. So in order to be differentiable, you have to be continuous first. So if you know you're already differentiable, that implies you're already continuous. Think continuous is the floor. Differentiability is any furniture. If the furniture's there, and there's probably already a floor holding that furniture up. So this is again a theorem. So if f is differentiable at x equals c, then f is continuous at x equals c.